Hello, our names are Benjamin Weir,
And I'm AJ Mallett.
and we are part of the Oral Roberts University team working on a flight simulator which integrates virtual reality with a Stewart platform. So in addition to addressing the larger work of the project, we've also been tasked with the implementation of the emergency cutoff switch, which is one of the key safety factors we have implemented into the controls of the simulator. And so our vision for this flight simulator was to create an interactive device that anyone, regardless of expertise, could use to experience the realistic feeling of flight. And the design that we chose makes use of all 6 degrees of freedom on a Stewart platform and is designed to be both a visual, auditory, and tactile representation of flight response to the commands of the user operating the simulator.
In addition to a few stock planes, we have enabled the simulator to accept student designs for planes so that the engineering students at Oral Roberts University can physically experience the designs that they have made in the university's aircraft design class.
And so in addition to students in the School of Engineering at ORU, we have designed the simulator to be able to be operated by non-technical persons to allow the project to be used by the Global Learning Center, which is a facility on campus which often sees visitors come through on tours of the campus. And so while we could talk about this part of the project for a much longer amount of time, it's not really the main focus of this presentation, which is because this machine has been designed to be used by non-technical operators under the supervision of someone trained in operating the machine. So none of these people necessarily being engineering students or being people involved with the design of the project. We are ensuring that the machine be able to be stopped instantly should anything happen to cause the machine to work outside of its normal range of operation.
Because the machine is controlled through Arduinos, we needed a physical component to stop the machine if it left its normal range of control, rather than implementing coding within the Arduino's instructions. Although we have not experienced any such malfunction yet, the thought behind this line of design is that if the flight simulator were to operate incorrectly, a programmed shutdown could not be counted on, as the issue would have to be occurring within the Arduinos, and therefore a mechanical solution would be necessary for those microcontrollers. In designing the emergency cutoff switch, we needed to keep the switch in line with the power supply and motors. This was so that in the event of an emergency, we could immediately kill the motor's power rather than turning off the power supply, as this would cause a time delay and the motors would continue to receive power for up to 5 seconds. By adding the emergency cutoff switch, we can allow the user to more immediately kill power should the need arise. However, the act of using a mechanical switch raises a new problem for a more immediate shutoff of the Stewart platform, which is switch bounce. Mechanical switches not only have the disadvantage of human response time, but also an effect on the Arduino due to the bouncing of the switch's connections.
And so just as an example of this issue, before we get into how we solved it, so when you drop a ball of clay on a table, what happens? It falls and it stays on the table without any additional movement. And so when you drop a ping pong ball on a table, it actually bounces multiple times before finally coming to a rest. And so the second example with the ping pong ball is exactly like what happens when a switch is thrown. Due to the mechanical nature of the switch, it typically bounces anywhere from 10 to 100 times in the span of 20 milliseconds as its connections hit. So in most cases, the Arduino works faster than the bouncing. And so the Arduino actually thinks that you're pressing the switch several times. And so this can be disastrous for the Arduino in a case of an emergency. And so even though it may turn off the machine, it might actually damage the Arduino and cause some just damage to the machine. And so when it comes to mechanical switches, there's 2 main variants, and so that's latching and momentary. And latching switches are pushed once to turn on and pushed again to turn off, like a light switch. And momentary switches are only on the on position while they're being physically pressed, more like a water fountain. And so for the purposes of this presentation, we're only going to be covering a latching switch similar to the one used for our emergency cutoff switch. And so the most common hardware debouncing circuits implement a Schmidt trigger. And basically that's a comparator with positive feedback. It only has 2 stable states, fully on or fully off. And this means that if the comparator is flipped on, you must come well back past the trigger point to flip it off again. So in other words, there is no trigger spot in the center where it flips on or off. And so this makes it convenient for dealing with bouncing states. However, a Schmidt trigger is a lot more complicated than what we wanted for the purposes of our project, so we made a much simpler version.
The circuit design that we chose is shown. It is the simplest version of the circuit we could build with the least number of components. It consists of 3 different resistors, a 0.1 microfarad capacitor, and a normal 3904 transistor, as well as the toggle switch and a relay for each motor. The values of the capacitors and the resistors are related in that the higher their values are, the longer the capacitor will take to discharge. This means that there will be a longer buffer to account for the bouncing. However, we cannot have those values be too high because we don't want to miss the switch actually turning on or off because of how long it takes for the capacitor to discharge. This concept is also known more familiarly as the RC time constant.
And so also shown are our before and after graphs. These are the measurements of the emergency cutoff switch. And so the first graph shows what the signal looks like without the debouncing circuit implemented, and the second graph shows the signal after implementation. And so notice the large number of rapid bounces on the first graph when the switch is only flipped once, but on the second graph, the switch is turned on and off twice with no sign of bouncing at all. And so thanks for watching, and we hope you learned something about our project.